Hey guys, this is section 11.8, Power Series. And I have a shout out to Zoheb. Zoheb, if you're watching this, you better email me because this is the section that you said at the beginning of the semester that someone told you you should be the most scared of. So we're going to debunk that myth and move forward with Power Series. If you don't know what I'm talking about, please ignore the intro to this video. Okay, what is a Power Series? So a power series is named because of, hopefully, obvious fact that it has powers in it and sort of looks like a polynomial, or looks exactly like a polynomial technically, but it's any series of the form Cn x to the n. So Cn is your coefficients, that's where the C comes from, and then x to the n. So the n in your series appears in both the coefficient and the power of the x. And in this case, x is a variable. CNs are the constants, of course, like we just said, called coefficients. And for each fixed x, so for each value you choose for x, this series is a series of constants, and we can test to see if that's convergent or divergent. And the interesting thing is, a power series could converge for some x and diverge for other x. So we're going to learn how we can test that. Okay, so the sum of the series itself is actually a function because you can put in different values for x. And again, this looks just like a polynomial, but the difference is that it's infinite. So it never stops with the terms, whereas your standard polynomial is something like a quadratic or a cubic or a quartic, whereas power series keeps going all the way to where n equals infinity. Okay, so for example, let's see your constants be 1, or your coefficients be 1 for every single n. Then the power series is just the geometric series x to the n. And we already know information about that. We know that this series converges when x is between -1 and 1, and then diverges everywhere else. Because of course this would grow out of control if x is larger than 1, greater than or equal to 1. So there's one example. And then here's an even more generic form for a power series. So the difference between this one and the first power series is this minus a. So what this is saying is you can center your polynomial around any constant a, and it's still a power series. So again, what this works out to be, if you list out the first few terms, still looks just like a polynomial, just a slightly more complicated one. Or if you're remembering how to graph polynomials from pre-cal, then this would be shifted over by a units, shifted to the right by a units. And what we call this one, if it's not centered at 0, we say that it's centered at a, or we say that it's a power series about a. Those are the two most common, in my opinion, ways to talk about this. Okay, what else? So notice that if x equals a, then this term would be 0, a minus a, and of course your series would converge because it would be the sum of an infinite number of zeros. And then also notice when n equals 0, which is the first term, you have c0 times x minus a to the 0. And remember, anything to the 0 is 1. So this first term would just be 1 times c0. And that's how you get your constant of your polynomial. Because remember, a polynomial is typically several x terms and then a constant. So that comes from n equals 0. Okay, let's look at an example. For what values of x is this series convergent? And our series is n factorial times x to the n. Remember that n factorial means n times every integer below it. So 4 factorial is 4 times 3 times 2 times 1. And whenever we see factorials, it's easiest to use the ratio test to test for convergence because most of the factorials will typically cancel each other out. So if we set up the ratio test for this series, we would have n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the n. Because remember, to set up the ratio test, you have a n plus 1 divided by a n. So the n plus 1 term divided by the nth term. Now, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, and so on. So if you were to write out a couple terms of this factorial, then everything in and below would cancel with the bottom factorial. So by dividing these two factorials, all you're left with is simply n plus 1. Everything else cancels. And then x to the n plus 1 divided by x to the n, you guys know how to combine those. You subtract the exponents. N plus 1 minus n is just 1. So all you're left with is an n plus 1 and an x. Now, the absolute value doesn't need to be around the n plus 1 because n is always positive. N goes from 0 to infinity. However, x is our unknown here, so that still has to have the absolute value. So the ratio test reduces all the way down to just n plus 1 times absolute value of x. Now we can finally apply the limit in the ratio test. As n goes to infinity, what happens to n plus 1? Well, of course, if n goes to infinity, n plus 1 also goes to infinity, which means this limit is infinity, no matter the x. So, by the ratio test, the series diverges when x is not 0. Why do we have to say when x is not 0? Well, remember, in order to use the ratio test in the first place, you have to make sure that the denominator is not 0. And in this problem, the denominator would be 0 when x is 0. N factorial can never be 0. Even 0 factorial is 1. So the only way this bottom is 0 is for x to be 0. So the ratio test says this diverges. This limit is infinity, thus it diverges when x is not 0. So the converse of that would be that it converges when x is 0. And that's all the information about this one. Diverges when x is not 0, converges when x equals 0. Okay, so interestingly enough, the main reason that we came up with the conventions for power series and rules around how they work is because it's often an easy way to represent functions that come up in the different sciences. And one of them that's discussed in this section is called the Bessel function. And it's written here on the screen. I'm not going to attempt to say that out loud, but there's a lot going on here. It's an alternating series, as you can see from the -1 to the n. And then we have x to a power, which is why it's a power series, and then some constants using n in the denominator. Okay, so we know that the sum of a series is equal to the limit of the sequence of partial sums. That's the definition of the sum of a series. So when we define the Bessel function, which is, again, this function in the middle of the screen, we define it as the sum of the series for every real number x, such that the limit of this partial sum is our Bessel series. So this bottom one here is the exact same information as the top one, only we switched variables to an I so that we can discuss the partial series. I'm sorry, the partial sum. So an interesting thing to do, because honestly, it's very difficult to look at this, this form of the series, is to write out the first few terms or the first few partial sums. If you plug in the next couple of terms, you get x squared over 4 as your second term, x to the 4th over 64 as your third term, x to the 6th over 2304, and so on. So these are the first 4 partial sums of the series. Okay, and here are the graphs of those partial sums. So if you considered the partial sums as functions, because they do have x's in them, then they're polynomials, which means you can graph them and look at them. So remember, every partial sum is an approximation to the sum of the series itself. So this is a way to see how is it changing as the partial sums get larger and larger. So S0, the first partial sum, is just the horizontal line at 1. And then S1 is the blue line, the upside down quadratic. S2 is the positive cubic, and then so on and so forth. So an overall complete graph as your partial sum gets larger and larger and larger is this pink line here, or this pink curve. Okay, so for all the power series that we've seen so far, the set of values of x that makes the series convergent has always been an interval. So now let's see the theorem that says, yes, that's always true, basically. So for a given power series centered at A, there are only 3 possibilities. Number 1 is the series converges only when x equals A. So this is an extreme case, right? Because x equals A means it's just the sum of 0. 0 plus 0 plus 0 plus 0, infinite number of times. Number 2, the series converges everywhere for all x. So that'd be kind of the opposite. So we have one extreme to the other. And then number 3 is the sort of an in-between. Number 3 says there's a positive number, capital R, such that the series converges if the absolute value of x minus a is less than that number and diverges if it's greater than. This number, capital R, this letter was chosen because we call it a radius of convergence. Because if you think about it, it defines an interval because of the absolute value and the inequality. So R is called the radius of convergence, and that leads to an interval of convergence. So in the first part of the theorem, in number 1, the radius of convergence is 0. And in number 2, it's the opposite. The radius of convergence is infinity. Okay, so the interval of convergence that I was just talking about is the interval where, or the interval of x values where the series converges. In the first case in the theorem from the page before, the interval is just a single point. And we don't typically talk about that as intervals, but you can write it that way. And in number 2, which is the exact opposite, the interval is infinite, negative infinity to infinity. And then in the third case, the inequality with capital R, that determines an actual normal interval like we're used to looking at. A minus R is less than x is less than a plus R. And that just comes from solving this absolute value inequality. Okay, when x is an endpoint of the interval, meaning x is a plus or minus r, anything can happen. Meaning the left-hand side and the right-hand side of your interval, we're not sure. So you typically have to test the endpoints of the interval of convergence. And that's why, if you look at the original theorem, there's no equal sign here, because we don't know what's going to happen right at the end. So that means there's 4 cases that can actually happen. You can have parentheses around both ends, which means it doesn't converge at either endpoint. You can have a bracket around just the left or just the right, or you could have brackets around both sides, which means it does converge at those endpoints. And that's something that you have to test for each one. Once you've found the interval of convergence or the radius of convergence, you still have to check the endpoints to find out if you're going to be using parentheses or brackets. And we've already technically seen that in the 4 examples we looked, 4 examples we looked at today. Or sorry, a couple of these are from the book. So compare this with the book along with the ones that we did in this lecture. So the very first one we looked at was the power series where the constants were all 1. And then remember, that's a geometric series. And so the radius of convergence would be 1. And the corresponding interval of convergence would be -1 to 1, because we know that this geometric series converges when x is between -1 and 1. So this is a geometric series that is also a power series centered at 0, because you can consider this to be x minus 0 raised to the n. So 0 is the center of your interval, and then it goes 1 in either direction. So the radius of that interval is 1. In the next example we looked at today, we had n factorial times x to the n, and we found that there's only one single point where this series converges, and that's the point where x equals 0. So that has a radius of 0. There's only one single point, so there's no radius at all, one number. Then x minus 3 to the n over n, this one is from the book, you find that the radius of convergence is 1. This is a power series centered at 3. 3 is our A. Notice our interval is centered at 3 and goes 1 in either direction. 3 minus 1 is 2. 3 plus 1 is 4. And in this case, I encourage you to look at the book to see this, but you do find that this series converges when x equals 2, but not when x equals 4. That's why we have parentheses on the 4 and brackets around the 2. And then the last one we looked at today, the Bessel function, we found that this series actually converges everywhere. The radius of convergence was infinity, which means this is centered at 0 because there's no minus or plus with the x, but the interval of convergence is negative infinity to positive infinity.